Today we're going to start with chapter 17.1, voltage regulation. Now, why do we want to regulate voltage? We want to get a constant and a fixed voltage, all right. How do we do it? We make use of voltage regulators to keep that voltage constant. Even if the load changes, and even if the load changes, and even if the input voltage changes, we want to keep the output voltage constant. All right, there's a few definitions. The first definition is line regulation. It's a change in output voltage divided by the change in input voltage if you want to express it in percentage times 100%. Or you can say line regulation, the change in output voltage divided by the output voltage divided by the change in input voltage. That will be my line regulation. All right. All right, what we want to show here is basically if my input voltage increases, my output voltage should stay constant. All right. There's the voltage regulator. We got a lot of different regulators. We will deal with that a little bit later. And here you can see even if my input voltage decreases, my output voltage also not going to stay. It's going to stay fairly constant. One important thing, this input voltage must always be larger than the voltage of the regulator. For example, if I got a 5-volt regulator, my input voltage should always be larger than 5, all right? If it's smaller than 5, the voltage regulator won't work, all right? Please keep in mind, the input voltage must always be larger than the output voltage. In the case of a 3-pin regulator, they normally say at least 2.5 volts higher than your output. Let's have a look at this example. Example 17.1, they say when AC input voltage of a certain power supply changes, the input to the voltage regulator decrease by 5 volts. As a result, the output of the regulator decreased by 0.25 volts. The normal output is 15 volts. Determine the line regulation in percentage per volt. Now there's a line regulation, it's delta V out divided by V out divided by delta V in. The change in output voltage is equal to 0.25 volts divided by the output is 15 volts divided by the change in the input voltage, and that will give me 0.333% per volt. All right. Then we're going to look at load regulation. In the case of load regulation, we will normally consider no load and full load conditions. All right. If I go and look at load regulation, I will consider low load, no load, and full load conditions. There's a voltage regulator. There I measure the load current. I measure the output voltage. All right. If the load current increases or decreases, you still increase, there shouldn't be any change in the output. But there is normally very small changes, and that brings us to the load regulation, the formula for load regulation. They say load regulation can be defined as a percentage change in output voltage for a given change in load current. One way to express load regulation is a percentage change in output voltage from no load to full load, all right? Normally, if you got no load, you will have basically maximum output. If you start loading the circuit, your output voltage should change, all right? And they say load regulation is equal to V no load minus V full load divided by V full load, all right? That's only things you should know there. Let's have a look at this example. Example 17.2, they say a certain voltage regulator has a 12-volt output when there is no load. IL is equal to 0. When there is full load current of 10 milliamp, the output voltage is 11.9 volts. Express the voltage regulation as a percentage change from no load to full load, and also as a percentage change for each milliamp change in load current. No load voltage, 12 volts, full load voltage, 11.9. The formula, V no load minus V full load divided by V full load is 12 minus 11.9 divided by 11.9, and that will give me 0.84%. All right. Now they say we must express it as a percentage change per milliamp. Then it's going to be 0.84 divided by 10, and that will give me 0.084 percentage per milliamp. All right. Right. Here is a method of solving this. I say sometimes power supply manufacturers specify the equivalent output resistance of a power supply, R out. That means this manufacturer will supply you with that. Now what we're going to do here, we're going to make use of Thevenin's theorem. What is Thevenin's theorem and why do we use Thevenin's theorem? Why do we use Thevenin's theorem? Can anybody tell me? Why do we use Thevenin's theorem? Or what is the use of Thevenin's theorem? All right, it's a method to help us to solve a problem. All right, and what is a Thevenin circuit? Yeah, but what is it? What does it consist? That means you can take any network of resistors and voltages and you can actually convert it to a Thevenin circuit. And what is a Thevenin circuit? It's a single voltage in series with a single impedance or resistance. All right. This is basically a Thevenin circuit. That you see that? And the voltage, the Thevenin voltage is equal to my no load voltage. That means if I don't have any load there, the Thevenin voltage is equal to the no load voltage. That means if I measure across the terminals, I will have my Thevenin voltage, and that will be equal to my no load voltage. And there they say V out is equal to V no load, because this is actually going to be a voltage divider. If I want the voltage across that, it's going to be RL over R out plus RL. All right. There they also give me my full load voltage. My full load voltage is going to be equal to my no load voltage, depending on the ratio of my resistors. All right. The full load voltage will be basically across my output. That's what, because it's I want to work out the voltage drop across my resistor there. All right. Now, if we substitute everything for the no load and the full load voltage into the equation, we know what is the formula for load regulation. And if we substitute everything in there, what actually will happen, everything will cancel out. And then at the end, I will say load regulation is R out over R full load. R out will be basically supplied by your manufacturer. Will give you the output of the voltage regulator, and then you can basically determine your load regulation, using that value given by the manufacturer. All right. All right, now we're going to start looking at our basic linear series regulators. The first one is going to be a series regulator, and now we're going to look at the series regulator. Series regulator is going to be a 3-pin regulator. It will normally have an input, an output, and we will connect your reference. All right, that is a series regulator. What will we find inside a series regulator? We will find a reference voltage. The reference voltage will be basically a Zener diode, a resistor and a Zener diode. We will find a control element. That will normally be a transistor. All right. My error detector will be basically like an op amp. and my sampling circuit will be a voltage divider. I repeat, reference voltage will be basically a Zener diode. Control element will be a transistor. All right. My error detector will be basically like an op-amp, and my sampling circuit will be a voltage divider. All right. Right, there's my complete linear series regulator. As I already mentioned, there's my reference. A resistor and a Zener diode will give me a constant voltage here. Error detector will be an op-amp. Control element will be a transistor. And my sampling circuit will be a voltage divider. All right.
So, does the reference voltage determine like what type of voltage regulator we're going to get? Like, for example, if it's a 5 volt Zener diode, is it going to determine that the voltage regulator is a 5 volt?
All right, we'll come to that. The reference voltage. We know about the op-amp. Everybody in the class should know the operation of op-amp at this stage. Is that right?
Yes.
That's right. Everybody should know it. If I got a 5 volt reference there, what should I feed back here? What does the op-amp always try to make the voltage difference there? Zero. That means I will feed back 5 volts. If the whole system is unstable, there should be 5 volt being fed back. Now, depending on the ratio of these two resistors will determine my output voltage, all right? That means if I got a larger Zener diode in there, or higher voltage value, the output voltage will be larger. But that will also be determined by R2 and R3. Now, what I'm going to do it very basic. We're going to work basically through this whole process, all right? And I'm going to put in all the voltages, and I'm going to put values in here. Let's say VZ. VZ is 5 volts. The Zener voltage, there's 5 volts across the Zener. Let's make R2 is equal to a 10 kilo ohm. Let's make R3 also a 10 kilo ohm resistor, all right? Now, again, what have I told you? The input voltage must always be larger than the output, all right? All right, let's assume, let's make V in plus 20 volt, all right? That's coming from my rectifier. DC 20 volts there. What will happen in the system? There will be a current flow like that, all right? If there's 20 volts, what's going to be across R1? What voltage is going to be across R1? 20. You want me to kill you, eh?
Yes, voltage.
What will the voltage be across R1? I always tell the students, what must you do? Think about Ohm's law, voltage and current law, and Kirchhoff's voltage and current law and Ohm's law. If you can apply those laws, you should always get the right answer. If there's 5 volts, what is the total here? 20. What is going to be there? Volts. All right. 15 plus 5, you can put in polarities if you want, is positive, negative, positive, negative. All right. You with me?
Yes.
All right, there's 15 volts. Now, what will actually happen? When we switch on the power, this transistor, this op-amp, there will be a positive voltage here. What will be there? At that instant, 0, all right. What is 0 with respect to positive voltage? Negative. Where will the output of the op-amp go? Will it go positive or negative? It will go positive. It will increase, all right. Doing what? Creating a base emitter current that's going to flow, all right. And due to that, I will get a much larger collector emitter current to flow, all right. All right, you agree? That means we switch on the transistor. Now the output voltage is going to do what? The output voltage is going to increase. Now to what value? It will increase until I'm feeding back what here? until I'm feeding back 5 volts here. When I'm feeding back 5 volts, if this point here reaches plus 5 volts, I'm feeding 5 volts back here. That means there's also going to be 5 volts, all right, due to the Zener diode. And now the whole story is going to be in balance, all right. What will the output be? If there's 5 volts across here, what should be across there? I'm asking, if there's 5 volts there, what should be across R2? There should also be 5 volts. That means 5 volts and 5 volts will give me an output of what? Plus 10 volts. All right. And now we can go a little bit further. What is the volt drop across my transistor or my control element? There's also going to be 10 volts across there. 10 plus 10 is 20. You can add it up. Everything will make sense. That's why Ohm's law and Kirchhoff's law, if you're going to apply those laws, you should always have the correct answer. All right, now the whole system is stable. Everything is stable, all right. But now let's do the following. We put a load here. We make it variable. We make it a variable load, all right. Now let's say we increase the current. We decrease that resistor value. Let's call it RL. We decrease the resistor value, and now we're going to draw much more current. When we do that, what will the voltage drop tend to do? Will it tend to increase or decrease? What do you think? It will tend to decrease. That means the output voltage, when I put a load there, a heavy load, the output voltage will tend to decrease. Now let's assume the output voltage decrease. That won't be a large decrease, it will be quite a small decrease. That means it will be, let's say, 0.1 or 0.2 volts, small decrease. But let's assume the output voltage decrease a little bit due to the load. That means what will happen to the voltage at this point? Will it increase or decrease? It will also decrease, all right. That means what will happen to that? It will also decrease. Let's say it becomes 4.9 volts, for example, a small decrease. When that becomes more negative than my reference, what will happen to the output of the op amp? Will it increase or decrease? Let's assume this becomes 4.9 volt. Is negative than 5. What will happen? The output will decrease. What input is that? Inverting. I'm more negative. Where will the output go? Wake up. It will go more positive. That means this base emitter current, that current, will increase. It will be a small increase. What will happen to the collector emitter current? It will increase, all right. What will happen to the output? It will increase. That means it will take it back to the original value. That is negative feedback, all right. It will take it back to the original value. That's how this is operating. The opposite, let's say you remove the load. If I remove the load, what will happen there? The output will tend to increase, all right? The voltage here will tend to increase. That will become a little bit larger than 5 volts. What will happen? This base current will become less. The collector emitter current will become less, and it will do what? It will take it back to the original. That means then this volt drop across this control element will also vary. All right. You with me?
Yes.
Any questions? Any questions? That is a series voltage regulator. And there's a gain formula for that, because if you go and look at that, that is a non-inverting amplifier. It's a non-inverting amplifier, and there's a gain formula for a non-inverting amplifier. The closed loop gain is 1 plus R2 over R3, all right? And then they give us the formula, but I don't want you to know the formula. I want you to know how the circuit is operating. And if you have a look at what we did there, they say V out is equal to 1 plus R2 over R3 times my reference. Let's go and have a look. R2 and R3 got the same value. That means 2 times, what is my reference? 5 volts. 2 times 5 will give me what? 10. That means we got the correct answer. Here's an example where they just use the formula. They say determine the output voltage for the regulator in figure 17.7. And there they use the formula, but there they got a different, they use a Zener diode of what, 5.1 volt. That means my output voltage is going to be 10.2 volts. Is there any questions? Do everybody understand? All right. Next circuit, short circuit and overload protection. I just want to show you, if there's variations in the voltages, if the input voltage decrease, then they show you how the negative feedback is operating. We basically did that, all right. Here they only show me the input voltage decrease. Well, then what should happen? The output voltage should also decrease, all right. And then they show us what is going to happen. It's going to basically rectify that. Or if my input voltage increases, the output voltage should also increase, but then due to my feedback, I will basically rectify the problem. All right. All right, short circuit and overload protection. All right, here in this circuit, it's also a series regulator. The only difference, we put this basically in, they talk about a current limiter. How does it work? Let me quickly show you how it's going to work. Now, if I put a load here, let's say we make that load variable. What will happen? We will get a current flow that will now be my main current flowing there. If that current becomes, all right, we will also have basically current flow through here to turn on my transistor. All right. Now, if this current here, that current reaches, the current in such a way that the volt drop across R4 reaches 0.7 volts. Due to the volt drop, because if the current through the resistor increase, what will happen? My volt drop will increase, right? When it reaches 0.7 volts, what will happen? I will basically turn on this transistor and I will take current from here through this transistor like that, all right? And that is going to limit my current. When that current reaches the volt drop, or the volt drop across R4 reaches 0.7 volts, Q2 will turn on and will take current from my error detector, and then it will limit that current, all right? Yes?
So when Q2 turns on, does Q1 turn off completely, or does this still work?
All right, you're asking me a question. Now I'm also going to ask you a question. If Q1 turns off completely, will there be any current there? No. All right, that means if you make the load such a magnitude that the volt drop across R4 becomes 0.7, it will keep it will keep that current or limit that current, all right. Even if I put a short circuit there, it will limit that current to that value, all right.
Yes.
Any other questions? All right, here they give us the formula for that, for my current limiting. They say IL maximum is 0.7 volts divided by R4. 0.7 volts divided by R4. That means if I reach 0.7 volts, that will determine my maximum current. Let's have a look at the example to illustrate that. They say determine the maximum current that a regulator in figure 17.9 can provide to a load. And there they show us I got a 1 ohm resistor there. And then if you work it out, 1 ohm and 0.7, that means 0.7 amps. Or 700 milliamps will basically be my maximum current. All right. That means if you draw, it won't be able to draw more than 700 milliamps. It will limit it at 700 milliamps. All right. Everybody with me? All right, the next one. A regulator with fold-back current limiting. We will normally use this type of regulator when we working with much larger supplies. That means when I talk about larger voltage regulators that can handle much more current, all right. They say in the previous current limiting technique, the current is restricted to a maximum constant value. Fold-back current limiting is a method used particularly in high current regulators, whereby the output current under overload conditions drop to a value well below the peak load current capability to prevent excessive power dissipation. The basic concept of fold-back current limiting is as follows, with reference to figure 17.10. The circuit in the green shaded area is similar to the constant current limiting arrangement in figure 17.8, with the exception of resistors R5 and R6. The volt drop developed across R4 by the load current must not only overcome the base emitter voltage required to turn on Q2, but must also overcome the volt drop across R5. This is the voltage across R4 must be VR4 is equal to VR5 plus VBE. That means to turn that thing on, I must have that volt drop plus that 0.7. That means the volt drop across R5 plus the volt drop across between the base and the emitter of Q2. That means you need VR5 plus VBE, otherwise it won't turn on. All right. I just want to show you what the fold-back technique looks like before we go to that. You see, here's my output voltage. My output voltage, my current can increase to a maximum. But if I go over the maximum, what happens if I create a short circuit, for example? When you create a short circuit, then the current is going to drop to a much lower level. I will be able to go to the maximum, but if I create a short circuit on the output of my voltage regulator, it will go to that. All right. They say in overload or short circuit conditions, the load current increased to a value IL max that is sufficient to cause Q2 to conduct. At this point, the current can increase no further. The decrease in output voltage results in a proportional decrease in voltage across R5. Thus, less current through R4 is required to maintain the forward bias condition of Q1, so that VR decreases, IL decreases as shown in the graph of figure 17.11. The advantage of this technique is that the regulator is allowed to operate with peak load current up to IL max, but when the output becomes shorted, the current drops to a lower value to prevent overheating of the device. Something else I want to point out on the series regulators. If you look at this series, I just want to show you something. If you look at this series regulator here, let's say I got a 15 supply, I got an input voltage of 15 volts. Let's say the output voltage, all right, don't worry about the values, but let's say the output voltage is plus 5 volts. All right. What is the volt drop across my transistor? I got 10 volts across my transistor. Everybody agree? No problem. But the moment I put a load here and I start drawing current, let's say I draw 10 amps, let's say I say IL. IL is 10 amps, all right. 10 amp flowing there. What is the power dissipation in my transistor? How do you work out power? P is equal to V times I. You agree? Now, the volt drop across the transistor is 10 volts. The current is 10 amps. What is the power? That means P, the power dissipation of the transistor, is equal to 100 watt. All right? And that is one of the big problems with series regulators. All right? If you start drawing a lot of current, you're going to get a lot of heat that's going to be dissipated in my control element. All right? If there is not a big difference between my input and my output and I'm drawing small current, no problem. But the moment when there is a large difference between my input and my output voltage, and I start drawing current, I will have a lot of heat that's going to be dissipated. And you can basically blow up the transistor or this control element. All right? You with me? Just remember it. Keep it in your minds when we go to other regulators. All right, we're only going to do the shunt regulator, then we'll be finished for today. 17.3. All right, a basic shunt regulator. All right, shunt regulator. There's a regulator. We need a resistor inside the circuit to basically create a volt drop if there's current flow. Again, what do we have? A reference voltage, an error detector, a control element, and a sampling circuit. All right. The error detector, same. Reference voltage is a Zener diode. Error detector is an op amp. Control element is basically a transistor. And the sampling circuit is also a voltage divider. All right. To have a look what's going on the output. Here's my shunt regulator. Why they call it a shunt regulator? Because my control element is basically in parallel with my input. All right. There is a resistor there just to detect, or you can say the control elements in parallel with your load. All right. All right. Let's have a look. What's going to happen here? Let's make it simple again. Let's say I got again a reference of 5 volts. All right. What do we want to feed back to get the system in balance? I want to feed back 5 volts. You agree? All right. How's it going to work? That means, let's say here's a current flow through there, through the load. There will also be current flow through there, and that will create a volt drop. Now, if I'm feeding back 5 volts here, then the whole system is going to be in balance, and there will be a certain amount of current flow. Let's use another color. Let's make it there will be a base emitter current flowing there that will cause a current to flow like that. All right, now my whole system is in balance. Everything is in balance. I got a certain output voltage depending on the ratios of my resistors. All right, let's assume I make this variable. I increase, or let's say I decrease my resistance. I increase IL. Let's say IL increases, becomes more, all right? What will happen? If IL becomes more, all right, what will happen? What will happen to the volt drop here? It will increase. If that volt drop increase, what will happen to the volt drop here? Listen, I increase IL. The volt drop across R1 will increase. You agree? What will happen to the volt drop here? Because that's going to give me my feedback. Anybody? What? Will it also increase? Hey, think. You S3 students. What will happen? Will it increase or decrease? What? It will decrease because this volt drop increases. That means the output voltage will decrease. The voltage here will also decrease. You with me? That decrease. That means this also decrease. All right. When that decrease, it becomes, let's say now 4.9 volts. It is negative. When that is negative, what will happen to the output? Will it increase or decrease? It will also decrease. When that decrease, my base emitter current will decrease, my collector emitter current will decrease. The current flow through R1 will do what? The current flow through R1 will do what? Anybody? It will decrease because this current decrease, that current decrease, that current decrease. The current flow through R1 will also decrease. All right. The volt drop will what? Decrease. When that volt drop decreases, the output voltage will increase. It will have the opposite effect. All right. And vice versa. All right. You with me? I hope so. Any questions?
What will actually increase this? Like I've missed out something. You said if IL increases.
All right, I say the load current increase. All right. When that increase, the volt drop across R1 increase. You agree? Because all the current flow through R1. That means there's more current flow. If there's more current flow, what does Ohm's law state? V is equal to I times R. R is a constant value. I increase. What is going to happen to the volt drop across that? Let's call it VR1. Let's call it I1. Let's call it R1. You agree? That increases, all right. What happened to the output if this, I got a fixed input. If that increase, what happened to the output? It will decrease, all right. It will become less. That means now the voltage here will also do what? Will become less, all right. That means now I had 5 volts there when everything was stable. Now it's, let's say, 4.9 volts. 4.9 volts is negative with respect to 5 volts. That means at the non-inverting input, the output here will also, output of the op-amp or the error detector will decrease, all right. When that decreases, what happened to this blue current? It decreases. What happened to the green current? It decreases, all right. What happened to the total current flowing there? It decreases, all right. When that decreases, that means that volt drop across R1 decrease. What is going to happen to the output voltage? It's going to increase.
will decrease.
Right, let me.
If the current decrease, obviously the voltage will also decrease.
Yeah, the total current here decreases, all right? That means the volt drop here decreases. What happened to the volt drop there? Increase. You with me? I hope so. All right. All right, there they explain exactly what I've told you. If you look in your book, they explain exactly what I've told you. If the one decrease the other, what's going to happen? Right. Same story. There they show you the currents. You happy? All right. Let's have a look at this. All right, there's a few formulas here. Let's quickly have a look at those formulas. There they give us delta IS, delta V in divided by R1. Delta IS is equal to minus delta IL. And then they say IL maximum is V in divided by R1. The maximum current that can flow there will be basically the input voltage divided by that resistor. All right. Because that will limit my current. Let's have a look at the example. Example 17.5. In figure 17.15, what power rating must R1 have if the maximum input voltage is 12.5 volts? Now they assume V out is 0. If I put a short circuit on the output, then the output will be 0. That means what will the maximum current be? Then I can work out, I can say VR1 is equal to V in is minus V out. V out is 0. That means VR1 is going to be 12.5 volts. Then they work out the power dissipation because they assume the output is 0. And when they work out the power dissipation of that resistor, they get a value of 7.1 watt. And then they say the normal standard wattage value will be a 10 watt resistor. They will put a 10 watt resistor in that circuit. All right. Up till now, we did the series regulator, we did the shunt regulator. All right. Next time we will look at the switching regulators. All right. And today's date, they make use of switching regulators. Why? Because switching regulators, you're going to use the transistor as a switch. All right. That means you switch it on hard and you switch it off completely. All right. Then you don't have that problem of that large volt drop across my transistor. But we'll come to the switching regulators next time.